All right, thank you very much. It's great to be here. Thank you all for coming to this talk. So the plan is I will talk a bit about how we can use tidal effects in binary inspirals to learn about interiors of compact objects, focusing on comparable mass binary systems. And I will also motivate again why it is so important to have accurate theoretical models and what we can do using analytical approximation methods. I will give a few examples of tidal effects that are being studied and some recent progress, and then end with an outlook to the remaining challenges and also the exciting future prospects in this field. So just to start, I think many of you are even more expert on all of this than I am, but we have several very interesting classes of compact objects that could be present in the universe. Well, for one, there are black holes, which in GR are just pure gravity, so no matter. They have an event horizon, and from the outside, they are completely characterized by just three parameters: the mass, spin, and electromagnetic charge, which is known as the no-hair theorems. But there are still many remaining theoretical puzzles with these kinds of black hole setups. And to resolve them, many proposed resolutions kind of modify either the near horizon structures or, in general, also this leads to violations of the no-hair conjectures. So definitely we would like to probe, are the black holes in our universe really these classical black holes with horizons and no hair, or are they different? Now, the second class of objects that are very interesting to probe are neutron stars. And that is because they involve not only strong gravity, but also extreme states of matter. In fact, the densest configurations of matter known in the universe, where gravity compresses the material to several times the normal nuclear density. And that represents a very large extrapolation from known physics. And it turns out the pressure that enables the matter to resist this extreme gravitational compression is mainly due to the strong subatomic interactions. So that provides us with a very good laboratory for testing completely unexplored regimes of nuclear physics and even QCD physics. And in addition to those kinds of objects, well, there could also be white dwarfs, which I didn't list here, but there could in addition be dark compact objects made of extra matter fields in the universe. For instance, dark matter or other beyond standard model physics fields, if they are present early on in the universe, just over cosmic times, they will tend to gravitationally condense into compact object-like configurations, still very fuzzy structures, but in some cases behaving very similar to compact objects. So these we also would like to know, do those exist in the universe or not? And how can we do this? Well, one way to do it is to put two such objects in a binary system, because they are very strongly gravitating, so they distort the space-time curvature. And as they orbit each other and are accelerating, that creates dynamical distortions in space-time curvature, and at large distances, those are gravitational waves. And a key point to note is that the gravitational wave signals that an asymptotic observer might measure are key fingerprints of the source field. So here you see some examples for black holes with different masses and spins, and how the signals differ in their details. But providing this mapping from signal details back to source physics is very nonlinear. And the way the data are analyzed and the source physics are being determined is that there are theoretical models that are cross-correlated with the data, and then very roughly speaking, whichever model with whichever parameters that best matches the data is thought to be the true source physics. So of course, it's a more sophisticated analysis, but the fact remains that our interpretation of this data is to a very large extent contingent on theoretical models. So clearly we need some models that are well, efficient to compute so that millions of them can be generated for each event, and also include all the relevant physics in a very accurate way. And to compute these models is actually a significant theoretical challenge because one has to solve the nonlinear Einstein field equations for the dynamical spacetime of the binary system. And that's a very hard problem. In general, different approaches have been developed over recent years and also over many decades before then. In this talk, I want to focus on analytical approximations. Those are limited to regimes where there's a clear hierarchy of scales in the system, but that is the case for binary systems during the early inspiral, because then the size of the objects is much smaller than the orbital size, which in turn is smaller than the wavelength of the asymptotic gravitational waves. And one complication is that in this case, we don't really have a single approximation that we can make for the entire spacetime and directly extract the gravitational waves. Instead, what we have to do is make different approximations adapted to different patches of the spacetime where different physics dominates, and then connect them all together. For instance, in regions of spacetime close to a compact object, we really have to use full strong field gravity. On the other hand, if we want to describe the interactions between two objects at very large separation, then those interactions at large distances can be described using post-Newtonian theory. And similarly, if we then zoom out much further and go to a limit where spacetime is almost asymptotically flat, then what remains is small distortions that are the gravitational waves, which can be treated in a different post-Minkowskian approximation. So this will be our strategy in this talk. And just to say, this perturbative information that we obtain in this way can be further resummed into state-of-the-art waveform models, for instance, a so-called effective one-body model. So I will not go into details of this model in this talk, but just to say this is one of the classes of models used for data analysis because it combines inputs from different perturbative approaches with information from numerical relativity. So our strategy will be to try to understand during a binary inspiral what kinds of effects of the interior structure of objects get imprinted in the gravitational wave signals. And there are many phenomena during the inspiral. I will further restrict the discussion to tidal effects. And the reason why these are especially interesting is because they actually correspond to the excitation of individual characteristic modes of the object. So in principle, that can give us spectroscopic information about details of the object's interior structure. And kind of the way to think about this is from the point of view of one of the objects, the companion appears to be orbiting and is exerting a tidal force that varies on multiples of the orbital frequency. Now, the orbit shrinks during an inspiral over a wide range in frequency. So at some point, the tidal forcing might get in resonance with one of the internal modes of the object, or even a non-resonant excitation where there's just an adiabatic deformation that is not oscillating, can also leave an imprint in the gravitational waves. And all of these effects are very small, but the nice thing about considering inspirals is that they accumulate over many cycles. So in the end, that can build up, even for small effects, some net information that can be measured. So let's look in a bit more detail into these tidal effects. I know you also already had a talk in September about tidal effect, but just to recap a bit, if it's too basic for you, please also tell me and I can skip some slides. But I was planning to discuss a bit the tidal response and then some further developments. So when a compact object, let's say it is non-spinning, is in a binary system, well, in isolation, it would be spherically symmetric because of the strong gravity. But in a binary, it responds to the curvature due to the companion. or in a Newtonian language, the tidal or gravitational force from one object is stronger on the near side of the other than on the far side, and so there's a gradient in gravity across the matter distribution, and the object deforms. But of course, we need to formulate this in a relativistic way, and we are especially interested in seeing how does the exterior space-time of the object deform away from a spherically symmetric space-time. And in the linear regime where tidal effects are small, this induced deformation will be proportional to the tidal field. So for a stronger tidal field, there's a larger deformation by some response function. And that response function depends on the details of the object. And to gain some intuition about what this response function is, it's useful to look at the limit, which we call the adiabatic limit, where the tidal forcing frequency is way below any resonance frequency of the object. And then it reduces to just a single number, which is the tidal love number. Here I denoted by lambda. Sometimes different notations are used for tidal love numbers based on different rescalings by the compactness. It's also known as the tidal deformability or sometimes tidal polarizability. All of these are roughly synonymous. And to give a bit more intuition about the frequency dependence, one can also consider, for example, a Newtonian uniform star, where the relevant modes are fundamental modes that get excited due to tidal effects. And in this case, we see this love number kind of characterizes how strongly these modes couple with the tidal field. But then there's a resonant denominator because the response gets larger when the system is closer to resonance. Okay, so let's stay a bit with these parameters that appear in this response function, which are the deformabilities and the mode frequencies. So let's first consider the tidal love numbers. So to really compute them, one has to look in detail, how does a relativistic compact object and its space-time respond to a tidal perturbation? And then extract the multipole moments at large distance. From that, one can infer these love numbers. So one has to really analyze the Einstein field equations and energy momentum conservation. And what one finds is that for black holes in classical GR in 4 space-time dimensions, these love numbers are 0. But for any other object or some modifications to black hole horizons or so on, one finds they're non-zero. And furthermore, for other objects, they also depend on the details of the interior structure. You see here some examples for neutron stars, where all of this subatomic physics that is poorly constrained at the moment leads to different equations of state, so different pressure density relationships, which are bounded by nuclear physics on the low density side and perturbative QCD on the high density side. But exactly in the regimes relevant for neutron stars, there are very large uncertainties, and none of the first principles approaches makes a robust prediction. And then going to compute these love numbers, one finds, if one looks at love numbers versus mass curves, which means each point on a curve is a different neutron star, and each curve corresponds to a different equation of state. One can see that there's a correspondence. If one knows love number and mass, one can work backwards to the equation of state if it is known for several neutron star configurations. But we are not yet there at the stage where we can say, oh, we measure love numbers, because all we have considered so far is the perturbed object itself. What is still left to do is to zoom out, go to the orbital scale, ask what physics affects the orbital scale, and zoom out further to go to the gravitational wave scale. And so as we zoom out from a perturbed compact object, we then kind of model it almost like a point mass because we're far away from it, plus some small additional correction due to the fact that it has some multiple. And this is also sometimes called a skeletonized description, where we have a central word line for the point mass dynamics, plus the additional multiple moments. And this is also what you would do in Newtonian gravity. In GR, it's a bit more subtle, but it's still possible to do it. So then we have an effective description that consists of a point mass term, plus a coupling of the multiple moments to the external fields. And then, instead of using this frequency-dependent response, that's not so useful for really computing inspirals because it diverges at resonance, which is unphysical. Whereas in a more physical setting, basically the modes would just be excited to some maximum amplitude and not diverge to infinity. So instead, what we do is we have some oscillator degrees of freedom corresponding to the multiple moments that kind of give the same physics as the response, but are more convenient for then computing inspirals. And these oscillators here are modeled by a kinetic term, which involves a total derivative along the world line, where tau is some evolution parameter along the world line, and a quadratic potential term, because we are considering small deviations from an equilibrium object. And these coupling coefficients in the effective description encode a lot of information about the object itself. And this can be seen, for instance, by saying, let's go to the adiabatic limit, where the kinetic term can be neglected, and look at the equations of motion we would get from this effective skeletonized description. We do get the same equation we had before, that the induced multipole is related linearly to the tidal field. So we can call this prefactor lambda and identify it with the love number that we computed from the perturbed object. Now, this kind of identification has, however, raised some concerns about potential ambiguities, because we are dealing with nonlinear GR rather than some effective field theory in flat space, where this kind of procedure is usually done. And I refer you to a dedicated paper by Sangrella on the ambiguity of relativistic tidal deformability for seeing details of this. What I want to mention here is that there is a way to avoid these ambiguities and make the whole construction more robust, which is by moving this identification between skeletonized action and fully perturbed compact object to null infinity, and considering gauge invariant scattering amplitudes, and using even geometrically motivated coordinates to make this identification. So that means for the perturbed object, we have to consider, instead of static perturbations, wave-like perturbations, and see how does it respond to such kinds of perturbations, and then match it with an effective skeletonized description at infinity. So in examples that have been computed so far for this case, the results were the same as before, but this is now a much more rigorous setting and much more watertight, with fewer ambiguities. Okay, so far what we have done is, okay, we have looked at the perturbed compact object, seen how does it change its exterior spacetime due to tidal perturbations, and found a description when we zoom out to large scales. So the next step is to put two of these skeleton descriptions in a binary system and see what are the consequences for the dynamics and gravitational waves. So in that case, as I mentioned, for the interaction between these two fully relativistic skeletons, we can use post-Newtonian expansion. So in that case, we end up with having to make a double perturbative expansion in finite size and post-Newtonian effects. And roughly speaking, if we focus on the dominant effects, which are due to the adiabatic limit, some of the energy will go into the deformation. The moving multipoles will also contribute extra losses to the system. And we can find an approximate result for the gravitational wave phase evolution, which the measurements are very sensitive to, well, which, not surprisingly, if we consider only one extended object and a point mass, is directly proportional to the lab number. And it also scales like a high power of the orbital frequency. So this means the effect is largest at high frequencies, so when the objects are close together. But it is important to note that the information accumulates over all frequencies. So you see here an example where we start at a gravitational wave frequency of 30 Hertz with, in this case, different neutron star models, and we require all the signals look the same in this smaller frequency window. And at a few hundred Hertz, we already see a small dephasing develop, and that gets even larger at higher frequencies. So let me maybe pause here in case there are any questions.
So, I mean, earlier you also mentioned that the body might get in resonance.
Yes.
With a perturbation.
Yes.
So, but what is the typical internal frequency of the object? Is it actually in the frequency range of the binary?
So that is an excellent question. Let me go to a few more slides, and then you will see if your question gets answered. Any other questions before I go on? Okay, yes. So as we said, we should take into account the fact that these are actually mode excitations. And so the modes that couple most strongly with these kinds of tidal fields are the fundamental modes. And their frequencies are, well, roughly order of magnitude, whatever frequency you can make up of the scales of the object itself. And the tidal forcing frequency occurs on multiples of the orbital scale. So for circular orbits, it means during most of the inspiral, these fundamental modes are not resonantly excited. But nevertheless, it turns out the resonance is actually really broad. So even if you're quite far from the resonance, you still get an enhancement of the tidal response compared to completely neglecting these mode effects. And you see this here on the y-axis is a measure of the response. On the x-axis is frequency, so the inspiral goes from left to right. It's just one particular example, so the numbers don't matter so much here. But you see the solid full response is larger than the strictly adiabatic response. And to take this into account, we then have to go back to the skeletonized action and include the kinetic term that we were neglecting before. And if you recall, it was written in terms of a total derivative along the world line, but it is nicer to write it out in terms of normal parameter derivatives along the world line. And then what one finds is that there's actually some frame dragging interaction that appears. So what does that mean? It means these dynamical multipole moments, they have a kind of angular momentum associated to them, which is roughly, in this case, Q cross Q dot, very roughly speaking. And that couples with the orbital angular momentum, which is roughly x cross x dot, or however you like to parameterize it. And that is a relativistic frame dragging interaction that arises. What you also see is that when matching the other coefficients, we see that these mode frequencies always appear together with a redshift factor, which depends on the parameterization that we use for the world line. But we then have two kinds of relativistic effects, the frame dragging and the redshift. And if we now again put this skeletonized description in a binary system, we then have to plug in for the tidal fields and the frame dragging couplings and the redshift, the post-Newtonian expressions, because we're assuming the bodies are at large distance. And in this case, these relativistic effects to the leading order, they almost cancel out. So in the first approximation, we assume they cancel out and then ask, well, how does the system then evolve through the resonance? Because now it is not so efficient to have all of these extra oscillator degrees of freedom in the system whenever we want to compute a waveform. So instead, we try to find an effective response, or integrating out these mode degrees of freedom which looks kind of similar like the frequency-dependent response we had earlier, but near the resonance, or yeah, in general, there are some modifications that depend on exactly how does the system transition through resonance and makes everything remain finite. And not surprisingly, this is the same as the solid line here, which is the same, or at least to a good approximation, the same if you include these oscillator degrees of freedom and numerically evolve the coupled orbit and oscillator motion, or if you use effective response. And this kind of effective response is also implemented in an EOB model called SEUB and RV4T. So that is also can then be used for data analysis. So to take a bit of a break from all the theoretical discussions, let me give you some example applications of all of this before I discuss a bit more theory about also including other modes. So, well, by now this is a bit outdated, or not outdated, but long ago event. This is still the best measurement of these tidal love numbers we have so far. It occurred in 2017, and it was probably a binary neutron star inspiral for sure. At least one of the objects was a neutron star. And this provided the first empirical measurement of these tidal love numbers. So that you see the tidal love numbers of the two bodies, some dimensionless measure of them in this two-dimensional plot here. And the gray band is the 90% contour of the measurement, where there is some uncertainty because different waveform models give different predictions. But anything to the left of this contour is consistent with the measurement at a 90% level. So that, of course, enabled many, many studies of analyzing what does this imply for the subatomic physics of neutron stars, which I don't want to go into in detail here. Because what you could also do in addition to measuring just the love numbers, you could also measure, for instance, the F mode frequency and the love numbers, which gives you a bit more information. On the other hand, you get penalized because you have more parameters in the signal model. So all of the accuracy of the parameter measurements deteriorate. But still, it is then interesting to consider, for instance, can we exclude the possibility that one of them was a boson star? Well, not fully, because we see in DASH are some different boson star models they have some quartic self-interactions, so there are parameters to play with. Some of them are still consistent with the data, and the neutron star models are on the solid lines, of course, only for selected equations of state. Any questions up to this point? Yes, yes.
And they're all like
Yes, yes. So both for the quadrupole and for the octupole was this study. Yeah, so there were 8 parameters in the model because we had it for each object. Okay, I don't see further questions. So now I will continue a bit with more theoretical information because, okay, so far we had the love number and the fundamental mode frequency, and we made many approximations. So let's go to relax a bit some of the approximations and include a bit more realistic. So, of course, the first thing could be to include more relativistic corrections where the redshift and frame dragging effects don't exactly cancel out. And the second effect is to include some spin on the bodies. And once one introduces spins, of course, there are many spin matter couplings that also appear. So here I'm just focusing on a subset of spin matter effects. which are those that affect the resonant denominators of this tidal response. So this is also important to keep in mind. Because, yeah, so for one, if the companion is spinning, then it introduces an additional angular momentum in the system. So it changes the frame dragging and gives there additional angular momentum couplings in the system. If the object is spinning, then it also modifies its tidal response, because if it's co-rotating with the orbit, kind of the forcing frequency it feels and to which it responds is lower than just multiples of the orbital frequency. And vice versa if it's counter-rotating. And again, we have to use an effective skeletonized action and determine some coupling coefficients. And here, the example has determined those coupling coefficients only for neutron stars to linear order in the spin. In principle, if we have data for perturbed compact objects, how the mode frequencies split due to spin effects, it could also be possible to do it for other objects, but so far this is what's available. And then, of course, the question is also, how good are all of these models? Am I just telling you something that is not really realistic, or is this kind of a reasonable approximation? And to test this, we then have to compare against numerical relativity simulations, because these are really without approximations. They capture the full nonlinearities, up to the fact that whatever the microphysics limitations are on the inputs, that of course they are also missing. But nevertheless, we can test these models against numerical relativity results. And here's just one example of such a test, which compares basically if all of these extra modifications to the resonant denominators are a reasonable approximation to the full result, and if we should now do a more detailed calculation to see how these effects impact inspirals. And what we see is that when varying parameters like the equation of state and the spins, which are all the different colors, change either one or the other, then the solid lines are this new description, including the resonant denominator modifications, and the dashed lines are the old description. And it seems kind of this model is giving or at least capturing the parameter dependencies more robustly over a wider parameter space. It's not conclusive, of course, because there are also other models that modify different aspects, but it's a good indication that we are on the right track. And we have also done many other tests, also against different waveforms from different groups, a neutron star black hole, double neutron star. Still, the models are not fully consistent with the numerical relativity, but at least we see it seems some of the parameter dependencies can be captured quite well. So that gives us now confidence to go to regimes where numerical relativity simulations are not possible, namely effects in the early inspiral and at small scales of the neutron star. And one such effect are so-called gravitomagnetic effects, because what we have discussed so far were so-called gravitoelectric effects, where there was a certain piece of the space-time curvature that induced mass multipole moments. And now in general relativity, there's an orthogonal piece of the space-time curvature, denoted here by Bij for the quadrupole, that induces current multipole moments in another object. And these kinds of tidal fields are relativistic. There's no Newtonian limit to them. So as a result, this gives rise to a very interesting phenomenology that is not the same as what we would expect from Newtonian intuition. So, for example, perturbation theory calculations that investigated again how does the object respond to such perturbations have already found, at least for neutron stars, that the relevant mode frequencies are proportional to the spin frequency. And for neutron stars, the spin is less than several hundred hertz. So these modes will for sure go through full resonant excitation sometime during an inspiral. Secondly, interestingly, it was also found that there are two kinds of tidal love numbers called sigma static and sigma rotational that depend a bit on different assumptions of the perturbed fluid. So now the question is, what is the impact of all of this on gravitational wave signals? And yeah, which combination of love numbers is relevant for the measurements? So as before, we go to the skeletonized description, and to see what this will look like, well, I've written it here, but I don't want to get lost in too many technical details here. What we kind of observe some interesting features in the sense that there's, for the oscillator, still a kinetic term, but there's no potential term. Instead of the potential, there's a nonlinear field contribution. And interestingly, also these coupling coefficients depend on both of the love numbers. And even more interestingly, it turns out when one then analyzes approximately what happens in an inspiral, it turns out there's one combination of love numbers describing the adiabatic limit long before the mode resonance, and a different one describing the adiabatic limit after the resonance. So that's also quite interesting, and that motivates really working out the effects in gravitational waves in more detail. It's true that these effects are small, so probably at the moment they're not so relevant, but they will for sure be relevant for next generation gravitational wave detectors. Any questions at this stage? Yes.
But this part here is based on post-Newtonian approximation.
No, this is fully relativistic. Yes. Yes.
Okay.
The next step where the post-Newtonian approximation comes in is once we plug in what this Bij field and this redshift factor and so on are in a binary system. That's a good question.
So you said there's a love number before and after the resonance?
Yes. Well, one combination of these two love numbers.
During the resonance?
No, if you look at adiabatic limits long before the resonance and long after the resonance, then it's different before and after.
Yeah.
Yes, this is a kind of effective love number that characterizes the adiabatic limit.
Okay. So does that mean when I have a single neutron star, say I couldn't say what is the love number of this neutron star, because it only makes sense to talk about the love number in the binary.
Yes, yes. Yes, if there's really some tidal perturbation to a neutron star. More questions?
What is the topology for a magnetic field? The magnetic field can be told about the particle when it's like a black hole for the magnetic field, or just another magnetic field?
So it's a gravitational field that has properties similar to a magnetic field. So it's not an electromagnetic. It's a piece of basically the dual of the Weyl tensor of the companion, certain components in the object's rest frame. Okay, let me also check. I think I still have a few more minutes. Yes. Okay, because so yeah, now I've described things in GR, and so I think I've only given a few examples, and we neglected many effects. We didn't include viscosity. We didn't consider other spin tidal couplings. Yeah, it's a whole long list of things we neglected. Also, other modes of the neutron star or another object. So clearly that is still work to be done, but instead of discussing more about this, because now you've kind of seen how the process works and the methodology and kind of how rich the problem gets once you start to think about effects you should include. So instead, I just want to very briefly mention some possible concerns about degeneracies with other unknown physics, because we want to probe unknown physics of the compact objects, but then there are additional uncertainties. For example, what I want to focus on is modified gravity. And again, I will only give some examples in a very narrow part of this whole question, which is to understand what the presence of scalar fields coupled with gravity can do to all of these tidal effects in a binary system. And to start with, let's consider first black holes and scalar fields in modified gravity, because they don't involve all the extra unknown subatomic physics of neutron stars. So without getting into too much detail about modified gravity, well, some of the theories beyond GR postulate that GR is kind of a low energy effective theory, and there could be higher order curvature corrections that come in only in high curvature regimes. So we wouldn't measure them, for example, in solar system tests. And one such class of theories is so-called scalar Gauss-Bonnet gravity, which involves an extra scalar field coupled with a quadratic incurvature invariant through a coupling function and some coupling constant. And the key point for the rest of this talk is that in this case, black holes can acquire some scalar hair, which means there's a scalar condensate that can form around and inside of the black holes. So we now want to consider what is the effect on binary system when there is this scalar hair on the black holes. And so in principle, because this theory or this class of theories considers massless scalar fields, which, okay, is arguable how realistic that is, and we have ongoing work to include mass terms. But nevertheless, even though the massless field falls off very slowly, so it's never exactly zero, outside of a few Schwarzschild radii of the black hole, the energy density is very, very low. So even effects like dynamical friction will not play a role because it is so dilute outside of this. Yeah, this kind of extra scale of a few Schwarzschild radii in this model. Now, now the interesting thing is that in a binary system, the scalar fields can also have tidal effects on each other. If one has two scalar condensates in a binary system, they can affect each other. And in this case, the interactions start at dipolar level. So the leading order effect is again an adiabatic effect where there's a scalar-induced scalar dipole moment, again proportional to the scalar dipolar tidal field with a tidal love number for the scalar dipole, which in this case is kind of not an independent parameter, but just depends on parameters of the theory and properties of the black hole. Now, then again, going through the skeletonization and effects on binary systems and radiation, we find, well, in addition, in this class of theories, in addition to these scalar effects, we also have to take into account the higher curvature and other scalar effects besides these tidal interactions, as well as post-Newtonian effects. And overall, we find modified energetics. And for the radiation, because now there are accelerating scalar charges, they produce scalar waves that start at dipolar order, which has additional contributions from the highly induced dipoles. And these scalar losses dominate in the early inspiral. But in the very late inspiral, gravity is just the most important component and gravitational waves dominate. And as a result, when calculating the gravitational wave signals, there are different parameter dependencies in the early and the late inspiral, which can potentially help us to discriminate this kind of scalar hair on black holes from modified horizon structures or perhaps dark matter clouds around black holes in GR. Of course, this remains to be further studied, but it's just a step towards all of this. Yes.
So these scalar most of them the following panels where the package stones S.
Yes.
So
Yes.
so could it be interpreted as noise instead of producing no that is in real data?
No, well, in the sense, we don't measure the scalar waves separately. We measure only how the orbit or the system evolves due to gravitational waves. So yes, it is true the signal will be lower amplitude, but it will still, well, okay, it depends also what approximation you make. But often, or at least in this case, we made the approximation that these modified gravity effects are small corrections to GR, so that we still have an almost GR-like waveform and then these extra corrections. So yeah, it really depends, I would say, on the assumptions you make and probably the kind of theory you consider.
It's also mean that it's a breaking point. Oh, in the whole case of this time.
Yes. Yes, but for instance, if we take 30 solar mass black holes, then if we have LISA in space, then LISA might see the early inspiral and ground-based detectors the late. So yes, I agree, it's probably more difficult, but I think it's also worth thinking more about how strategies could be developed to do it. Yes, yes. But I have to say that all of these approximations are only valid for comparable masses. Yeah.
I guess it's a minor detail about why the scalar radiation is the first leading order is dipole. Like, could we have monopole radiation with a scalar field?
No, it's again it's similar to electromagnetism, where you also don't have monopolar radiation.
Sending a scalar field can have monopole radiation, can't it?
You mean kind of like some breathing modes or something, or?
Yeah, like a spherical symmetry, I would think it could be, but
yes.
It's a minor
so
detail.
at least in these theories, not. It starts at the dipole. Yeah, we can maybe later look in more detail why that is.
Yeah.
I don't have an immediate answer.
Okay.
Maybe someone else in the audience knows.
Especially with the symmetry of binary system. If you have like something collapses in spherical sense, you have monopole. You can have
yes,
monopole
okay.
radiation.
Okay. Yeah.
Yes.
I see. Yes, you don't have a time varying monopole, I guess. Yeah, okay. Okay, thank you. All right. Maybe, okay, let me just briefly mention now that we have seen the scalar tidal effects for black holes. It's also interesting to ask, well, what now if we have scalarized neutron stars and what kinds of degeneracies can arise? Now, in the class of theories I just discussed of the scalar Gauss-Bonnet, neutron stars don't develop a scalar condensate, but there are many other classes of theories where they do, and the simplest case is scalar condensate theory. And it turns out, because now everything is coupled, the subatomic matter, the scalar matter, gravity, there are now actually three kinds of tidal love numbers and kind of couplings one has to take into account. There's the pure scalar sector we saw for the black holes also. There's the pure tensor sector we saw earlier in this talk, and then there's a mixed one because now for example, induced tensor protocol depends not only on the tensor tidal field, but it is also through all of the nonlinearities induced by a scalar tidal field. And to each of these, it has different response coefficients. Similarly for the scalar one. And now that makes it a bit more difficult to extract to relate these coefficients to the perturbation theory calculations and extract the microphysics encoded in them. But already these expressions suggest how to do it in principle. Well, we should look at the tensor quadrupole evaluated at zero scalar tidal field to get the tensor log number, and at zero tensor tidal field to get this mixed scalar tensor one, and so on. So ideally, we want to have some way in the perturbative calculations to set to zero different tidal fields and then extract the relevant response. But that's a bit difficult in practice because what we control are boundary conditions in the interior of the star, which is highly nonlinearly related to fields at large distances. But nevertheless, it is possible to find ways to combine different boundary conditions to extract this information. And then, well, we find some results. I think the details are not so important here, also in the interest of time. Definitely, it will be interesting to study further possible degeneracies with equation of state and this modified physics. We still are working on computing the effect in gravitational waves. This is just for the perturbed object itself. Also interestingly, these mixed scalar tensor love numbers are negative. So let me then end with kind of the outlook. Well, just now, the observing run of the detectors actually resumed again after a break where they were making further improvements, at least for LIGO. They resumed. And what we can expect in the coming months even is higher precision measurements of nearby sources and also just a greater number and diversity of events. So that also means we have to continue to develop theoretical models because we surely don't want to be limited by systematic uncertainties or missing interesting events because the models have shortcomings. And this will be especially important for the next decade, where really we will have precision measurements and completely signal-dominated data sets, both for the ground-based detectors of the next generation, the Einstein Telescope and Cosmic Explorer, and for LISA, the planet space-based detector. So in conclusion then, I've only discussed a small aspect of all of the interesting gravitational wave science, namely how we can use signals of inspirals to learn about interiors of compact objects through tidal effects, where again, that was limited. I did not give a comprehensive discussion of all of the effects, of course. I also argued there's now an exciting future ahead in the field with larger and more precise data sets to come, but that also means really in the future, we will be limited by theoretical model uncertainties. So that has already motivated a lot of progress, also brought in people from other fields that bring in new tools or new ideas for what kinds of effects we might be able to look for or should consider. And still much work remains to be done to really make sure our models are good enough to fully realize the science potential with gravitational waves. So that's it. Thank you very much.
Okay, we have a few minutes for some more questions, if there are any. Yes, go ahead, Hans.
So I want to come back to the love numbers with the resonance.
Yes.
So as I understood, basically that means a love number changes during the inspiral.
Well, the effective love number, once we remove these oscillator degrees of freedom. So in terms of the perturbed compact object, well, at least within our approximation, the love number is a fixed coefficient.
Oh.
But then, well, it also depends what you call love number, but then the frequency dependence of the full response changes during the inspiral. So here, this kind of changing response was kind of dividing out the love number. I don't know if that makes sense.
So what does this then mean with regard to this LIGO plot where they infer the love number?
Yes.
So I mean, there they only get the love number from from the inspiral phase,
Yes.
kind of, so is that then true love number, or how should I now see this plot?
Yes. So what is that? I know you mean this plot here.
Yeah,
Yeah. So what was done here was, okay, so besides this model with the F mode included, there are also other models that are either calibrated to numerical relativity or make other modifications. And they have as the only parameters the love numbers. So, and in addition, this model, what I showed here, was also used, but for neutron stars, there are kind of quasi-universal relations that are nearly independent of equation of state between F mode frequencies and love numbers. So this model was reduced to just depend on love numbers. And similarly, the other models by construction depend only on love numbers. And that was used here in this plot. And then in this next plot, we said, okay, don't use the universal relations, but see what we can learn. That was kind of what was done.
so basically, I guess it means the love numbers that I get from this plot, or the constraints,
Yes.
I should really only see them within the model they have used.
No, because once you relate here the F mode frequency to the love number, you've kind of, your model depends only on the love number. And then it gives, yeah, the information you get is really for the love number, if these universal relations hold. Okay, really okay, or? Okay.
Just later before the end, you showed those plots. You said that some the love numbers in this case are negative.
Yes.
And what's the difference in the interpretation between positive and negative?
Well, so they are defined by in terms of this Lagrangian, which is the skeletonized Lagrangian of the system, and well, also here in the response. So if that is negative, this will be a plus sign, and similarly here, and here will be a minus sign. Yeah, then as I said, we are still working out the consequences for the gravitational wave signals. I mean, usually in Newtonian intuition, well, what it would mean is instead of deforming kind of oblately, it deforms, or whatever it is, prolately or something like this.
Small question, like regarding the calculations in this game, because like you're talking about the skeletonized section, which is like a contribution, right? And when you added spins, I don't know, for my part, motivated by point particles, right? Like there's this, when you added spin for the
Yes.
particles,
Yes.
there is like the choice of frame is reduced to a speed supplementary condition in that case. I don't know if there's
Yes.
some ambiguity here in the choice of the spin or something like that, or just those two examples are not comparable, like I don't know.
Ah, okay. Yes, so this I mean, in principle, if we are talking about some observable, it shouldn't matter the spin supplementary condition used, because it should, if it's an observable, then it should be invariant, even under choices.
Okay, you mean like forgetting the log number?
Yes, I think so. But yeah, we didn't investigate what is the effect of using different spin supplementary conditions. Because it is also the effects in the binary system are then computed using post-Newtonian theories for the interactions. Yes, but it's a good question, given also that we have talked about ambiguities before, then it...
Yeah, like that is interpreted in my understanding like a choice of word line within the extended body,
Yes,
and then
yes,
you take
yes.
the limit.
Yes, exactly. Yeah, it's for the skeleton.
Yes.
it kind of defines the center of mass, let's say.
Exactly,
Yes, yes.
Good.
But this should not matter if we are talking about truly invariant observables.
Yeah, yeah, yeah. Okay.
Yes,
But I guess that is an expectation until like you actually
yes,
compare different ones,
we
right?
should test
Somehow.
it. Yes, indeed, yes.
Sure. One more quick question.
So I want to ask about the scalarized movement stuff.
Yes,
So there, as you said, we try to practice disentangle the contributions
yes,
from the fluid and from the scalar field.
yes,
And you said, okay, you set one component to 0 basically, but I wonder how you can set it to 0 because they always appear together and they're always deformed in conjunction.
yes. But what we want to set to 0 are these external tidal fields. So from the asymptotic space-time, we extract, looking at the fall-offs, we extract the induced moments and the external fields. And we want to find solutions where one of these external fields is zero. So that requires looking both at the tensor sector and the scalar sector simultaneously to see how can we set this field to 0. And as I said, since we don't control the boundary conditions asymptotically, we really have to work with the boundary conditions in the interior and find independent solutions that we can then linearly combine in this asymptotic region to set to 0 one of these tidal fields. So that is kind of the strategy.
Okay. So but the solutions themselves are non-linear.
Yes, the solutions, yeah, it's always, usually the solutions, you never have a solution that is exactly 0 tidal field. You then combine different linearly independent ones to achieve this.
If you enjoyed the video, like and subscribe.